Now we will derive the expression for pressure of ideal gas. We have a cube of side length L and of area A. First of all, we will calculate the length covered by or distance covered by the molecule in del T time. So, in time del T, the distance covered by the molecule is, if Vx is the speed along x direction and take the time del T, then from formula of speed, the distance equal to Vx into del T. Vx into del T. This is the distance covered by the molecule in del T time. Now, let's calculate the volume of the cube. It is nothing but area into length, where area and length is what? Vx into del T. This cube encloses some gases and the total number of molecules of that gas is capital N. Here N is what? Total number of gas molecules. And N, small n is the number density. Small n is the number density. And where small n is equal to capital N upon volume. Capital N upon volume. From here, we can calculate the formula for capital N also, that is capital N equal to small n times volume. If you put the value of volume calculated earlier in that relation, we will get a final relation of total number of particles of that gas enclosed in a cube, that is capital N equal to small n into A Vx into del T. This is expression for total number of gas molecules enclosed in this cube. As we all know, the gases have random motion, therefore they have net average motion in a particular direction, either in x direction, z direction or y direction. And due to this reason, when particles travels from any one side, the total number of particles does not reach the any side. So here one assumption is made that is half particle reach this wall and hits the wall. So we will take the total number of particles which hits the wall is what? Is about to half of the total number of particles. That is total number of molecules which hit the wall. Such particles which hit the wall will equal to half of the total number of particles enclosed in that cube. That is n upon 2. That is half of the total number of particles. That means we will get a value small n A Vx del T upon 2. This number of particles hit this wall. Now we will calculate initial momentum, or this calculation only for one molecule of gas. For one molecule of gas, initial momentum is equal to mass of one molecule, that is small m, into speed of molecules along x direction. This is because particle travels along x direction, that is Vx. Final momentum, mass cannot be changed, that is m, and V speed also is the same, but direction is reversed. That's why we put minus over here. So we have initial momentum, final momentum. That's why we can calculate change in momentum, change in linear momentum, that is final momentum minus initial momentum. And we have the value of initial and final momentum. Simply we will put the values of initial and final momentum and get the change in momentum. So final momentum is what? Minus m v x, and this is the minus of formula, and initial momentum is m v x. As we see both the terms in negatives, that's why they will add up, but the sum will be in negative. So minus 2 m v x is the change in linear momentum for one molecule. One thing we have to clear out here, the minus sign state what? The minus sign state that this change in momentum is offered by all on the particle. So the change in momentum by molecules on the wall is that is del P is equal to 2 m v x. This is what? By molecule on the wall. Now we will calculate total momentum change of all the particles which hit the wall. We have the total number of particles which hit the wall is this, and change in momentum of one molecule is this. We will simply take the product of these two and get the total momentum transfer of molecules, and we will represent total momentum transfer here by capital Q. So we have 2 m v x for momentum change of one molecule, and total number of molecule, that is n, small n, a v x del t upon 2. To cancel out 2, we have n m v x square a del t. This is the total momentum transfer of molecules which hits the wall of the container. Now we will calculate force. Force is equal to, from Newton's second law of motion, force is equal to change in momentum by taken time, and here change in momentum is capital Q and taken time is del T. Also calculate pressure. Pressure is equal to force upon area, and put the value of force over here. We will get A del D and Q. value of Q is N M Vx A del T and upon A into del T. Del T cancelled out each other. A cancel out each other. We have small n Vx square. This is the value of pressure. But this is not a final result. Here Vx is not same in every direction, or you can say Vx is not same along x, y, z, or in different direction Vx is different. So we will take the average value of Vx square. Therefore, this result becomes small n capital M Vx square bar. And how we calculate the Vx square bar here? That is Vx square bar, that is average of Vx square, Vx1 square, Vx2 square plus dot dot plus Vxn square upon n. This is the formula for Vx square bar. As we know, the gas enclosed in this cube is isotropic. And what is the meaning of saying isotropic? Isotropic means its property is same in every direction. So, as it is same in every direction, so we can write the value of Vx square bar equal to Vy square bar and Vz square bar, that is Vx square bar equal to Vy square bar equal to Vz square bar. So we will again calculate this value Vx square bar. So Vx square bar equal to Vx square bar Vy square bar Vz square bar by 3. If you confused how you write this formula, then we will check out it. As you know, all three are the same, so just put Vy square bar equal to Vx square bar, Vz square bar equal to Vx square bar. We will get 3 into Vx square bar upon 3, 3 cancel out, rest Vx square bar, and this side also Vx square bar. So this is nothing, this is Vx square bar. We will consider this value as V square bar. So we have Vx square bar equal to V square bar by 3. We will use this value over here and we will get a value, final result, that is P equal to 1 by 3. We separate out 1 by 3 firstly, n small m capital N and V square bar. This is the final expression for pressure of an ideal gas. And here this is known as mean squared speed. Mean squared speed. Mean squared speed. We will also calculate pressure for ideal gas in terms of density also. We will calculate this over here. We just put the value of small n and small m and we will get the final result in case of density. So small n is equal to n upon volume, and we will use the concept of total mass of the gas molecules, and that is represented by capital N. Mass of one molecule is small m and total number of particle is capital M. That's why total mass of the particle is capital M. From here we will calculate small m. Small m equal to capital N upon capital M upon N. Just put this and this value and that's in this equation. So P equal to 1/3 and in place of n, small n, we will use value capital N upon volume, and in place of small m we will use capital M upon capital N, and we have V square bar. Capital N cancel out each other, and mass upon volume give the density. So P equal to 1/3 rho V square. This is the pressure of ideal gas in case of density case. So we have the final expression for ideal gas pressure. One is this and this. Thank you.